Hello all, a warm welcome to the next session on electronic devices. In the previous session, we had discussed about how switching basically happens in the cutoff region and in the saturation region. That is, my transistor is said to be in the on condition, that is in the saturation region, then it is approximates to that of the behavior of switch being in the on condition. If my transistor works in the cutoff region, then it approximates the behavior of the switch which is in the off condition, right? Now, under the same topic, we have one more topic that is being left out, which is the specifications of the switching transistors. So what is the specifications of switching transistor? Before going into that, first let's try to understand what is a switching transistor. Now, a switching transistor is the one which is used to switch between the cutoff region and the saturation regions at a very faster rate or at high frequency. If the switching of the transistor happens between the cutoff region and saturation region or vice versa, then such kind of transistors which is used to behave so is referred as switching transistors. Now, when I consider these switching transistors, we have to look into certain specifications which is with respect to that of the time at which the switching takes place. Yeah. So, there are two conditions we know, the transistor being in the on condition and the transistor being off in the off condition. Now, let's try to consider a plot which is ECE, that is the collector current versus the time, and here we can see there are totally 6 time factors that we are considering, that is TD, which indicates the delay time, then TR refers to the rise time, then T on indicates the on time, that is the time period which is required to turn on the transistor. Then comes the other factors like TSD, which indicates the storage delay time, and the storage delay time we have already come across in the previous session, right? And then TF indicates the fall time, and the sum of these two will indicate the off time, that is how much time you require for the transistor to make the transistor to come from the saturation region to that of the cutoff region. So, if I want to write down the expression for T on, how can I represent the expression for T on? It is the sum of the delay time and the rise time. Now, how can I define delay time? As you can see the amount of time it takes for the collector current to reach from 0 to 10% of the maximum value of IC. So, 0 to 10% of IC value, how much ever time it takes to reach, and that time is what we refer as delay time. Done. Now, when I consider rise time, how can you define rise time? It is easy, right? Just look into the plot. What is the time? It is the time that is required to reach from the 10% to that of 90% of IC value. So, how much ever time that you require, that amount of time is referred as rise time, and the sum of these two is referred as on time. Yeah, once it reaches this value, that value is referred as the current which is absorbed at the collector at the saturation region. That's why I have referred as IC sat, which is 100% of the IC value that you have to look into. And this is the region where I tend to say my transistor is in the on condition. Now, once the transistor is on, in the previous session we had looked into what will happen. See, what am I trying to do here? We are operating in the saturation region. When the device is in the saturation region, what is the drop that is absorbed in the collector junction? It is very minimal, right? So, all the drop is absorbed across the load. Therefore, how will I represent this current? IC, if you remember, it is represented as VCC divided by RL. And in the previous case, by considering 40 volts and 5 kilo ohm, we had got around 8 milliamps of current. So, that is how we will get the saturation current, that is the maximum current that can you can achieve across the collector region. Done. Now, the next thing that we have is called as TSD. What does this TSD indicate? It is the storage delay time. Now, what does the storage delay time indicates as? There are certain charges that are stored in the base. Now, once I want my transistor to switch from the saturation region to the cutoff region, the charges that it has needs some time to get decayed to 0, right? So, that period of time before it starts decaying to 0. So, that period of time is what we refer as TSD. Done. That is the time that is required to reduce from 100% of IC value to that of 90% of IC value, that is called as TST. Then comes the fall time. What does this fall time indicates? It is 90% of IC value to 10% of IC value. How much ever time you require, that time is referred as fall time, and the sum up of these two is referred as the off time. So if I want to represent the equation for off time, how will I represent that? It is TSD plus TF. And these are the specifications that you have to consider or you have to look into whenever I am considering the switching transistors. And this completes the sixth topic, that is switching in the BJTs. Now we are left out with one more topic, which is about other effects that can be seen in the BJTs. Remember, I have told you one word which is called as secondary effects. While understanding the working principle of BJTs, we assumed that let's assume that the second order effects here it is seen is nullified, or there is no second order effects being considered. Now we'll see and try to understand what are the different second order effects that comes into picture when I consider a BJT, and how will it impact the performance of the BJT. There are many second order effects or secondary effects that is being seen in the BJTs, but in syllabus we are only interested in 3 of them, and that's what we'll try to discuss in today's session. Now, what is this other important effects is nothing but the second order effects that is being seen in the BJTs. Now, you might think, what is the second order effects? See, when we try to understand the behavior of the BJTs, we had come across the drift component, the diffusion components of the currents, and then we also looked into the current equations that we come across in the BJTs, and all those are nothing but the first order effects of the BJT. Now, this second order effects are the ones which does not raise a concern, and it is not of that much importance until and unless it is trying to alter the behavior of the device. See, if in case this tries to alter, if there is a change in the base width, if that tries to alter the behavior of the device, and that kind of phenomenon comes under the second order effects. Getting my point? If there is a change in the dimensions of the device which tends to alter the behavior of the device, then that is considered to be a second order effect. So similarly, whatever the effects, whenever there is a change in the device parameters or something in the device that alters the behavior of the BJT, then that kind of orders or that kinds of effects is what we refer as second order effects. And this is not of much prominence until and unless that changes occurred. Only when you start seeing that changes in the device being made, then only these second order effects comes into picture, or they try to have their prominence. Yeah. So we'll try to see the 3 different other important effects that can be seen under BJT. The very first one goes as follows, which is the drift in the base region. Now, as you can see, what am I focusing on here? It is the base region of the PNP transistor that I am looking into. Now, before going into trying to understand this, for this, in order to understand the drift that is happening in the base region, you need to understand how the doping is basically performed in order to obtain a P plus NP transistor. Yeah, I'll just give a brief introduction how basically it happens. See, whatever the doping that I want to perform, in order to do that, first what I'll try to do is, I'll try to have a semiconductor which is purely made up of a p-type material, that is being the background. So what is that being background? I indicate as I have a base, Okay, so I have a silicon material or any kind of semiconductor material. For that semiconductor material, what I have done, I have completely doped with a p-type material. So if I want to dope it in order to make it as a p-type material, then which kind of doping I have to do? It is the acceptor doping that I have to do, right? So let me just try to represent that doping profile over here. So let me just consider the axis upon which I am trying to represent the doping concentration to be as X. Done. Now what is that I am doing? I am considering a constant doping. I am trying to provide, I am trying to do a uniform doping of an acceptor atoms, which is Na, and if I do this, what is that layer I will be forming? It is the p-type layer that I am forming, and that let me represent this layer to be as a background, because this is considered to be the underlying layer upon which I am trying to diffuse the rest of impurities in order to make it as an n-type material or a p plus material. Done. Now across which I am plotting this is being plotted across the doping concentration. And this is measured in the log scale. Done. Which is the kind of transistor I am trying to obtain. It is P plus NP transistor. Now once we are done with this, now what I will try to do is, to the existing p-type material, now I am trying to provide the donor impurities into it. Now when I try to infuse the donor impurities into it, then the profile of the donor impurities goes as follows. Yeah, and this is what? This basically indicates what? The donor impurities that I am putting up. Then what I will try to do is, I will try to further put up some amount of acceptor doping into this, and let me represent this to be as Na. Now please be careful and try to understand. See, I will mark certain points here. Done. Now when you see this particular region, out of the acceptor doping and the donor doping, which one is dominating? It is the acceptor doping that is being dominating, right? So if the acceptor doping is being dominating, then which kind of material is I am trying to obtain? It is a p-type material that I am getting. Now is this acceptor value that I have, is it very much greater than that of the initial acceptor doping that I have done? Yes, that means this region whatever I have, it is nothing but your P plus region. Done. Now let me try to observe this particular region, this particular window. Now in this window, what is your donor doping? It is greater than that of the acceptor doping. That means which kind of material it forms? It is the n-type material. Therefore this I will be representing as n-type. And then till this point it goes. After that, as you can see, my Na is dominating when compared to that of Nd, which indicates that this forms which kind of material? The P type of material. Now what makes this as P plus is this Na is way higher than that of the initial acceptor doping that I have done. Therefore this is become heavily doped emitter region, this becomes the moderately doped or lightly doped base region, and this becomes the moderately doped collector region. And this is how I can represent the doping concentration across the axis X. If in case I want to represent the same in the one dimension or in the cross sectional view, then it goes as follows. We have a sharp P plus emitter region, then comes the N region. And what is this N region being doped of? Nd. What does this region being doped of? Na. And this indicates what? The p-type region. Done. Now from where I am trying to measure the distance, that is at the very corner edge of the P plus, from here like this towards the right I am moving. If I want to represent the same, then I have to start from here, which is the 0 axis, and this is how I will be measuring the doping concentration across the axis X, and that is what I am trying to represent. I hope all of you are clear with this cross-sectional view as well as this log scale, which indicates how the doping concentration is varied across the distance. Now, why am I considering this plot is, see, when you observe the base region, is the doping that is being performed in the base region is uniform? No. It is trying to vary, right? What is that happening? At the emitter junction it is high, whereas once it reaches the collector junction it is reduced. That means this is an exponentially decreasing doping concentration that I can see in the base region. Now, this is the one which forms the drift in the base region. Now, what does that mean? I will tell you in a while. Before that, let me just try to plot this doping change in the doping concentration in the base separately. Now, how can I represent that graph? It is as follows. Now, let me, which is the region that I am considering? I am interested in the base region. Therefore, let me consider 0 to WB. What does this indicate? It is the width of the base region, right? Now, what is that I am trying to represent? It is the doping concentration. How will I represent the doping concentration? Please see to the equation. It is Nd minus Na, because we have both the concentrations that is available, right? So, if I take up the difference, then I will be able to clearly get the doping concentration across the whole width of the base region. Now, at the initial stage at 0, this is what the doping concentration I'll be having, that is at this point I am trying to represent. Whereas, as I tend to move along the width of the base region, what is it trying to happen? It is trying to decline or decay, and it is not reaching 0. Please note that point, it is not reaching 0. This is the point at which the doping concentration is 0. There is still some value that is being seen, therefore I am stopping right here, and let me represent this value as the doping concentration which is absorbed at WB, and this indicates the doping concentration which is seen at 0. Done, and this is what I have clearly depicted over here. Yeah, and why the slant like this I have represented is because there might be little recombination that can take place at the base region. By considering that, I have considered this particular exponentially decaying function. Done. Now, why is that I am considering all these factors? See, if in case I consider a base region, in this base region, if I don't have an uniform doping, then what will happen is, try to understand this point. So, if in case I observe at this point of time, which is being dominated, it is the Na concentration which is more than that of the Nd. That is, this is the emitter region, right? Now, that is the emitter junction, right? Now, when I consider this point, that is the collector junction, now which is being dominated here, Nd value is little more dominated when compared to that of Na. Post this only, Na keeps dominating. Done. Now, here the holes are the ones which is dominating at this exact point, and this is where the electrons are being dominated. Now, there is a variation in the charge concentration that I can see. As a result, what is happening is, there is a built-in electric field that is being absorbed, and that electric field is from where to where? Here from, it is always, remember, the direction is from positive to negative. Therefore, that built-in electric field which is absorbed in the base directs from the emitter region to that of the collector region. Yeah. Now, because of the electric field that is absorbed due to the variation in the doping concentration across the base, what is basically happening? Whenever there is an electric field intensity, what happens? So, if this is the direction in which the electric field intensity is present in the base region, whatever the holes that is present in the emitter region, will it be get swept to the collector? Yes, at the very faster rate. Yeah, that is what will basically takes place. So, this will in turn make the drifting of the holes from the emitter to that of the collector, and that is what this topic basically means. That is the drift which happens in the base region. Why it is happening? Because there is a non-uniform doping that takes place in the base region. Done. Now, if there is a drift that happens in the base region, what does that result in? It results in the decrease in what is called as transit time. Now, you know what is transit time. It is the amount of time it takes for any of the charge carriers to move from one point to another point, right? Now, as I have a variation here, this electric field will make the holes to get swept to the collector at a faster rate. Therefore, what happens to my TT? It tends to reduce. So, is it an advantageous factor? Yes, it is advantageous, right? At a faster rate, I can make the holes from the emitter to be swept to the collector because of change in the doping concentration, because of the electric field that is built in, because of the drift factor that is being taking place in the base region. Therefore, we can say that the transit time that is involved will tend to reduce. Now, if the transit time reduces, then I can make use of this in the devices which operates at higher frequencies. Getting my point? So, that is where this particular drift in the base region, second order effect comes into picture. Now, there are few equations that you have to go through. Let me just try to represent that. What is that I'll try to represent is, see here we have a diffusion factor as well as the drift factor that is involved because of the non-uniform doping in the base. Yeah. So, by including both of these at equilibrium condition, if I try to represent, okay. Now, what is that I am trying to represent? At equilibrium, I am trying to represent both the electron drift and electron diffusion components at the base region. So, at any point n across this x, at any point n in this region, if I try to measure, the current that I can see is given as Q into A into mu n into n xn into E of xn plus Q into A into dn into d of n xn divided by dxn is equal to 0. We know at equilibrium the sum of the diffusion currents and the drift current is equal to 0. Therefore, I have equated it to 0. Here, which current I am considering? Remember, this is the electron current at the base region. That is what I am interested in. So, what does this Q indicates? It is the charge of the carrier. A indicates the cross-sectional area. Mu n indicates the mobility of the electrons. N xn indicates the doping concentration or the doping that is happening in this xn region. And then E of xn indicates the electric field that is being seen, that this electric field, no need to represent that in the diagram, I have just shown it for your reference. So, this whole thing, see when I include the electric field, then which component it belongs to? Does it belongs to the drift component or the diffusion component? It is indicating the drift component. Done? Now, what does this indicate is, see, as I move across the distance, what is happening to the concentration? It varies, right? That is why I have considered this particular factor. And this dn indicates the diffusion coefficient at the n region. Q and A we have already come across. And this factor indicates the diffusion factor. Done. Now, if in case I have a doping concentration which is uniform across the base region, then what is that? Results in what happens to this differential term? Since there is a variation, we had considered the differentiation term. If the uniform doping is there in the base region, what happens to this whole term? It will tend to equal to 0. Now, as a result, this whole term goes away and the only component that is left out is the drift component. Done? Now, using the same equation, now what I will try to do is, I will try to represent the expression for the electric field intensity which is absorbed in the base region. Yeah, for that what I will try to do, I will keep it here and this I will try to move it to the other end. So, QA into mu n into n xn into E of xn is now equal to minus Q into A into dn into dn xn divided by dxn. See, always remember, whenever you are writing the expressions, once you are done writing the expressions, make a habit of listing out where what does I, n, x, n indicates, what does q indicates, what does a indicates, what does mu n indicates. I am telling it orally, but it's your duty to mention what all these factors indicates whenever you are writing the answer. Done? Now, so once I am done with this, what will I try to do? I will try to cancel out q and a, and then what is that I want? It is E of xn, right? So how will I do that? It is minus of dn by mu1 into 1 by n xn into d of n xn divided by dxn. Done? So this is one of the expressions for the electric field that is absorbed in the n region across the x direction. Now, a little alteration I can do. What is that is, since dn and mu1 are constants, it can be equated to kT by q. As a result, what will be now the electric field intensity equation? It is minus of kT divided by q by 1 into n xn into d of n xn divided by dxn. Therefore, I can write the electric field intensity in two different forms. One is with respect to dn and mu(n) and other with respect to kT by q. Done. And one key point here I have to say is, whatever this doping that I told, how it is being performed, that type of doping is called as graded doping. Done. That is, first making it as a p-type, which is a background, upon which I will be doping with a donor and then increase with an acceptor impurities. Done. And this kind of base that I have formed because of graded doping is called as graded base region. So all these are the key points that you have to mention whenever you are writing the answer, if in case the drift in the base region is asked. Done. I hope all of you are clear. So these are the factors that you have to clearly mention, and don't forget to mention about the tau t, because that is what I am trying to focus, and these equations with what does each of the terms indicates. So this is regarding the first important factor which relates to the second order effects which is absorbed in the BJT. And why is this? Because it is because of the non-uniform doping that is absorbed in the base region. Now let's try to look into the second kind of factor. The second kind of factor also relates to the base region, and the third as well relates to the base. So all three of them which I am considering is relating to the base region. Now let me consider that here let me have a P plus N P plus region, or you can consider P plus NP as well. In your textbook they have mentioned both the emitter and the collector is being heavily doped and the base is being lightly doped, and that is what I am considering here. If in case you want to consider the P plus NP, that also you can consider, no issues. Now let's try to represent the depletion regions. See, focus on this because this is where the important factor lies. See, this is heavily doped, therefore what happens to the width? As I already mentioned, it has to be very short. The depletion region which is near to the P plus, whereas which is near to the base, as it is lightly doped, this can be a little wider. Done. Here also it can be little wider, the same distance that you have to follow, and here it is at the lighter note. Now if in case I want to measure the distance of the base, how can I measure? This is the x which is through which I am measuring, and this is 0 and this is WB. Now this is the condition when I am considering the collector base junction is at 0 potential. Done. No doubt on this, because we all know all these factors, right? The only key point that you have to remember is the N is being lightly doped. Now what am I trying to do is here, as I tend to increase the reverse bias potential across the collector base junction. What is that I am trying to do? I am trying to make the collector junction to become more reverse biased. So if I want to indicate that, all I can do is consider this condition. What is that condition? VCB is very much less than minus KT by Q. And what does this indicate? I am trying to increase the reverse bias potential at the collector junction. Now tell me, as I tend to do that, what happens to this particular, this is still forward bias, we are considering for a normal mode, this is still forward bias, but what happens to this particular depletion region? Will it be widened or will it remain the same? Obviously, there is a change in the depletion width. Will it increase or decrease? Since it is reverse bias, what happens to the depletion region? It gets widened, right? Now, as it gets widened, since my N is lightly doped, this width tends to extend towards the base region. It tries to occupy the base region, and then there is a little extension that I can see in the P plus because it is heavily doped. Now let me just try to represent this variation in the width of the base. Now tell me, whatever the width of the base that I had seen in this case, will it be greater than that of the other case or will it be smaller? So this case, we have the base width which is greater than when I tend to increase the reverse bias potential. Getting my point? Why? Because this depletion region is tending to encroach the N-type material. It is trying to occupy the N-type base region. As a result, the base width that I could see tends to get reduced. And let me try to depict that in the figure. And it goes as follows. Let me just try to represent it below it so that you can clearly make out the difference. Now what are these regions? P plus, N and P plus. Now what happens to the effective base width? Now tell me, the same axis. Now here the base width was right here, but now it is reduced, and that reduction is what I am trying to represent. Starting from this, where the junction is being formed, that is where the emitter junction and collector junction is being formed, this is referred as the metallurgical width of the base. And how will I represent that? It is being represented by LB. There is an encroachment of the reverse bias junction into the base region. So whatever the extended reverse bias depletion region that I have, let me mark that to be as L. Done. Now how can I represent this LB? How can I relate my LB and WB? And it goes as follows. And my L is square root of, it is directly proportional to the square root of VBC. So these are the two equations that you have to represent within this particular diagram. So this indicates that how basically the base is getting narrowed because of this being lightly doped, and that is what we are discussing, which is called as base narrowing. Now what is happening to the width of the base? It is getting changed. Therefore I can also name this factor as base width modulation. And there is an other name for the same as well, and that other name is referred as early effect. So if in case they ask you to explain what does early effect mean in case of BJTs, then this is what you are supposed to explain. Now we understood how this extension of the reverse bias junction is taking place. Now when this happens, what exact changes you can see in the behavior of the device? See, previously the width of the base that was available was more. As a result, whatever this junction is forward bias, this junction is reverse bias. As a result, whatever the holes that was there, when it tends to get diffused here, few of them would get recombined with the electrons which is present, and the rest would reach this point, right? Now, what is happening to the base that is available? The width is reduced. The width is reduced means what happens to the recombination that takes place at the base? Even that tends to reduce, which indicates more number of holes now can reach from the emitter to that of the collector with less recombination that is taking place at the base region. Got this point? And that in turn indicates what? The IC current. What is happening to the IC current? It is increasing, right? That means how much ever holes I am trying to inject at the emitter, or out of which majority of the holes are reaching the collector and very few are recombining at the base region because the width is very small. Therefore, there should be an increase in the collector current that I can see in the device. So, let me just represent that increase in the collector current by considering the characteristics. Yeah. Now, one more thing that I want to represent is the length, that is this extension of the reverse bias depletion region towards the base. That length is given by the equation L is equal to 2 into epsilon into VCB, 2 into epsilon into VBC divided by Q into ND to the power half, and this is the equation which represents how what is the width of which the depletion region has penetrated into the base region. Now what I'll try to do, I'll try to represent the increase in the collector current, and let me represent that increase now. Now let me consider here the common emitter configuration. See, please note this point, the kind of configuration that you are considering. Here the graph is being written for a common emitter configuration. If that is the case, then IC is the output current and minus VCE is the voltage that I am interested in, the reverse bias voltage, therefore negative I have written. Done. Now, how is the current being increased? So since it is a common emitter, I am plotting with a variation in the base current, and this is the equation that relates both of them. So how can I relate that? This is when I have to draw a little downwards, and this is indicating for IB is equal to 0. Now can I write the straight lines? No. What is happening to the collector current? Because of the decrease in the base width, it is increasing, right? So I cannot write as a straight line, but instead what will I have to do? I have to show in the increase that is happening in the collector current. Purely without early effect, this was the graph that I was supposed to write. But due to early effect, what is happening to the collector current? It is increasing, right? And that increase is what I am trying to represent in the graph. Now, if in case I want to know at which voltage this is basically happening, then all I have to do is trace back this in the backward direction, and all these will meet at a particular point, and thus voltage is referred as VA, which indicates the early voltage, which basically indicates the voltage at which this early effect can be seen. That is the voltage at which you can see the tremendous increase in the IC current. Done? Now, one more thing you have to understand is, as I tend to increase my VCB more and more, what will happen? So this depletion region will try to penetrate more and more into the base, and it will reach a point wherein it will completely occupy the base region, and there will be nothing as base region. Instead, you'll be having a depletion region, because of which there is a direct transit of the holes from the emitter to that of collector. Now, is this a good phenomenon? No. What is this phenomenon referred as? We have already come across this. What is this called as? It is called as punch through phenomenon. And whenever I want my device to operate, I don't want this to operate at punch through. What is this punch through? The complete punch through. It is the complete encroachment of the depletion region at the reverse bias collector junction being occupying the base completely. And this should not happen. Getting my point? So that is what you are supposed to remember. And this is all about the base narrowing, or which is also referred as base width modulation, or the early effect. And this is the second order effect that we have considered under the BJTs. We have one more, that is the last second order effect that we have. Let me try to discuss that. Yeah, the condition, please remember, it is less than, very much less than minus kT by Q, and this is the condition that I have represented. So what happens to the width of the base? It tends to reduce, and this is your L, this is the metallurgical width of the base, which is represented as LB. Now the same phenomenon that I am considering to understand the third second order effect, which is avalanche breakdown. It's very simple. See, we had considered what is punch through, right? So before punch through, there is one phenomenon that takes place which is called as avalanche breakdown. Now what is this avalanche breakdown is? See, we have already come across this phenomenon when we considered the diodes, that is the PN junctions. The same phenomenon occurs here as well. That means as I tend to increase, that is the collector base potential at the collector junction, what happens to the reverse bias potential? It tends to increase, which in turn increases the depletion region that is absorbed across the base, which tends to try to occupy more and more, which tries to encroach more and more the base region. Now, when this is happening, what is happening to the electric field that is being absorbed? This is the direction in which the electric field is seen. Now, this electric field becomes more and more intensified. So as a result, what happens to the charge carriers? So whatever the minority carriers in the P plus, which is the electrons, tends to get drifted to the N region. Whatever the minority carriers, that is holes, tends to get drifted into the P plus region, and we saw how the collector current increased in the previous case. Now what am I interested in is here, whatever the minority carriers that is present in the P plus, when they tend to get drifted to the or get swept to the N region, they are at higher energy, right? So they tend to collide with the atoms that is present in the N. Once they collide, they make the electrons which is present in the valence band to come out, which makes the covalent bond that is present. As a result, it is trying to generate what is called as EHP, that is the electron hole pairs. So when the electron which is here tries to come and hit, if you remember, the electron when it is here, it tries to come and hit, what is being generated? An electron and a hole pair is being generated. You remember these diagrams? Yeah. So what is that I am trying to do? Previously I had a single electron. Now because of the increase in the electric field intensity due to what? The increase in the reverse bias potential, I am trying to get more and more number of electrons. The charge carriers are getting increased, and this is nothing but the multiplication, carrier multiplication, which takes place. And because of this carrier multiplication, what happens to the current that is absorbed in the device? It tends to increase, and that is where the breakdown happens in the reverse bias, and that kind of breakdown is what we call as avalanche breakdown. Yeah, and the kind of multiplication, the carrier multiplication that takes place is referred as avalanche multiplication. Now, if in case I want to represent that in the characteristics, then it goes as follows. Let me just consider both the cases, that is the common emitter and the common base configuration. What is the output current in both the cases? It is IC. This is the zero axis. So I have considered here common emitter configuration. We know it is plotted IC versus minus VCE, and this is the region where the breakdown happens and enormous increase in the current starts absorbed, and that is what I have shown for different values of IB. As I tend to increase the IB, how IC is increasing tremendously, and this region where the breakdown happens is what we refer as B into VCEO. Now what does this B into VCEO indicates is, it is the collector junction breakdown voltage, which is seen in which configuration? Common emitter configuration, by keeping which terminal as open? That is the base terminal as open, and this O here indicates the base terminal being open. This is the breakdown voltage that is absorbed in the collector emitter, common emitter configuration with the base being open. Now when I consider the common base configuration, we know it is plotted for minus VCB versus IC, yeah, and for different values of IE that I can see. Yeah, as I tend to increase the IE value, what happens to IC? Once it reaches about to reach the breakdown value, what will happen? The current starts tremendously increasing, and that slight increase is what I am trying to show here. And this is the case for I equal to 0. As I tend to increase IE, IC increases a little, and then it will increase near the breakdown region. And then what does this B into VCBO indicates? It is again the collector junction breakdown voltage. In which configuration? The common base configuration. So the base is common, and what is left open? That is the emitter is being opened. So at this point of time I can find out what is called as a breakover voltage. And this is regarding both the configurations, that is common emitter and common collector configuration. What you can make out? The tremendous increase in IC as soon as it reaches that breakdown voltage. Done? Now, if in case I want to represent that in the equation form, let me try to represent it. So, IC is equal to what? Alpha N into IE plus ICO. You remember this equation we had come across? See, I'll just write a portion of it. Sorry, this was ICO and this was alpha N into IE. Remember this, we had applied a KCL at this point. These two are incoming currents and this was outgoing current. In which model we had considered? One of the Ebers-Moll model. So that is the equation that I have considered here. Okay. Now, is it the same? Whatever the IC, will it be same as that of this equation? No. There is increase in the IC value because of the carrier multiplication, which is also called as avalanche multiplication. That factor have to be included, and that is what we refer as M, which is the multiplication factor. Now how will I represent that multiplication factor? It is alpha N into IE plus ICO 1 minus VBC divided by D into VCBO to the power N. Done? And this equation is for which configuration? The common base configuration I am considering. Done? Don't forget to include the multiplication factor, which indicates the avalanche breakdown, which is the second order effect. I hope all of you are clear till here. Now let's try to see how to obtain these values, that is the breakover voltages. Yeah. So in order to do that, first let me consider, anyways I have written for common base configuration. For common base configuration, what is left open? Emitter is left open, right? Therefore, what happens to the IE value? It is 0. So if IE value is 0, if I substitute that in the above equation here, let me not consider that complicated equation. Instead, I will consider only this equation. If I tend to substitute IE 0 in equation 1, what will happen to IC? It is this term becomes 0. Therefore, it is just M into ICO. And this equation will help you out to find out how much should be the breakover voltage that I have to see in the common base configuration when I keep the emitter to be open. Done? Now, what is the other configuration that we have? It is for the common emitter configuration. Now, if in case I consider the common emitter configuration, what is left open? The base is left open. Therefore, IB is equal to 0. We know the basic equation. What is IE is equal to IC plus IB. So, if I make this as 0, therefore, what is IE is equal to IC. Now, let me just substitute that here. So, 2 in 1 if I substitute, then what happens? IC is equal to, in place of IE, I will substitute as IC plus ICO into M. Now, let me just try to solve it. IC, I will shift IC term to the one side. So, now if I take IC as common factor, what will be the term? I will be getting M into ICO divided by 1 minus alpha N into M. Now, this clearly depicts, here this clearly depicted the collector current as a function of multiplication factor with the reverse current that is flowing across the collector region. Now, what does this here indicates? It is the collector current which is flowing for the common emitter configuration, which in turn will help me to find out what is the breakover voltage. Done? Now, as you can see in this particular equation, what is alpha? And it is the current ratio, current transfer ratio, which is observed in the normal mode, right? So, which is almost approximately equal to unity. 0.99 will be the value of alpha. What happens to the beta value if that is the case? Even the beta value will be very high. So, those are the key points that you have to remember. What happens to the current transfer ratios in these cases? So, it will be very high, whereas for beta it will be very high, whereas for alpha it is approximately equal to 0.99. Now, if in case this whole term becomes equal to unity, if my multiplication factor is approximately equal to unity and this if it is of 0.99, then what happens to the denominator term? 1 minus 1 gets cancelled out and anything divided by 0 will be infinite, which indicates that if my multiplication factor is 100%, then the current that I can see at the collector junction is almost infinity, and that is what this equation basically represents. Done? And this is all about what is called as avalanche breakdown. So, what are the phenomenon that takes place? Because of the high electric field intensity, the electrons, that is the minority carriers which is present in the P plus, tends to get drifted towards the N region, that strikes the atoms which is present here and generates the secondary electron hole pairs, which again strikes, creates the third one, and similarly it goes on. As a result, the carrier concentration tends to increase, and this results in what is called as avalanche multiplication, which makes the current to break down at certain point and tend to increase tremendously, and that breakdown points we have represented for two different configurations, that is common emitter and common base configuration, and we have also seen how to represent IC values for both of these cases by considering emitter open for the common base configuration and base open for the common emitter configuration. Done? And in this equation we understood, as I see that if the multiplication factor is 100%, if it is equal to unity, what happens to this term? It will be 0, which indicates that the collector current is almost infinity. Yeah, and these are the points that you have to remember under the avalanche breakdown, and these are the factors, that is the drift in the base region, then comes the base narrowing, which is also called as base width modulation or early effect, and the third factor, which is avalanche breakdown. So, all these three are the second order effects that we have discussed for BJT. There are many more second order effects, but we will not be looking into those because it is out of the scope of syllabus. Yeah, I hope all of you have enjoyed learning BJT and its important aspects. And also the second order effects that is involved in the BJTs. The one topic which is left out is BJT fabrication, which we will cover up when we consider the 5th module. Thank you one and all. Happy learning. Bye for now.